We are going to discuss about the special cases in the elastic collisions. We already derived the final velocity in the one-dimensional elastic collisions. The equation for V1 and V2 given here. The two bodies are having equal masses. When it is hitting, they are exchanging their velocity. If we take this one as an ideal elastic collision, if masses are same, then they exchange their velocities. On this concept, one elementary particle was discovered. Can you tell me what is that elementary particle discovered on this concept? The masses are same. They are moving in the same direction with initial velocities u1 and u2. After collision, they are moving in the same direction with velocities v1 and v2. Then the equations v1, v2. If you write m1 is equal to m2 and simplifying, we get v1 is equal to u2. That means first body is getting the velocity of initial velocity of the second body. For v2, the velocity is equal to the initial velocity of first body. That is, the velocities are interchanged. Head-on collision between two spheres of equal masses. In the elastic collisions, they interchange their velocity. So in the diagram also we have explained the masses m and m after collision move in the same direction with velocities v1 and v2. So finally, what we arrived is masses are equal. They exchange their velocities after collision. When masses are equal, they exchange their velocities. See here, only one is coming out because if masses are same, they are exchanging velocities. How they will be asked in the examination? Two identical balls A and B are moving with velocities 0.8 meters per second and minus 0.3 meters per second. They collide head-on elastic. Find their velocities after collision. See, we can calculate V1, V2 by using the equation. We can apply the principle of the special case of the collision. That is, if masses are equal, they exchange their velocities. Therefore, simply the second velocity minus 0.3 becomes first. Similarly, 0.8 meters per second, the first body velocity becomes second body velocity. That is, first option is the correct option. Similarly, they may give a neutron moving with 10 meters per second, hitting a proton at rest. What are their final velocities after collision? Head-on. So simply the answers will be, need not to calculate V1, V2. Simply we can say neutron will come to rest and proton gets velocity of neutron, that is 10 meters per second. Because masses are equal, they exchange their velocities after collision. Like that, we can save the time in competitive exam. Here you see, a lighter body is hitting heavier body at rest. A lighter body is hitting a heavier body at rest. What is happening? Heavier body will be still at rest, but lighter body is bounced back with the same velocity. Here the ball, lighter body, hitting a wall at rest. What is happening to wall? Nothing happens. And it is still at rest, but the ball is coming in the opposite direction, the same velocity. That we want to demonstrate here, demonstrated here, and we want to show mathematically also. What is going to happen? Heavier body will be at rest only, but lighter body bounces back. How to prove it? Right? In the equations of V1 and V2, U2 is equal to 0. By neglecting M1, the equations, by neglecting M1 in the equations, we can arrive V1 is equal to minus U1 and V2 is equal to 0. Thus, in this case of collision, a lighter mass M1 with heavier sphere M2 at rest. The velocity of lighter sphere is reversed, but the heavier sphere remains at its rest only. Similarly, when a ball of mass m1 is falling from a certain height, after striking the ground, it rebounds with the same velocity. It's also another example for how it will be given in the examination. A neutron is hitting a nucleus at rest, a heavier nucleus at rest. What is happening to the nucleus? Nothing. But the neutron comes back with the same velocity in the opposite direction. So, like that, you have to understand these applications. When a lighter body is hitting heavier body at rest, heavier body will be at rest only, but the lighter body bounces back with the same velocity. The best example here is the Rutherford alpha ray scattering experiment. When an alpha ray is hitting gold foil directly, that is head-on collision, then it is bounced back. So you can see the experiment of this Rutherford. When alpha particle is hitting directly, that is head-on collision with the gold foil or gold nucleus, it is bounced back with the same velocity. That is observation given by Rutherford. The case of atomic structure. How it will be given in the examinations, competitive examination. When an alpha particle is hitting gold nucleus or lead nucleus at rest, what is their final velocities? The gold or lead nucleus will be at rest only, but the alpha particle comes back with the same velocity. That is, the direction changes. The velocity is given as 20 meters per second. Now the answer is minus 20 meters per second because the direction was changed. Like that, in competitive examinations, this type of questions will be asked. The heavier body will be moving in the same direction, but the lighter body is gaining double the velocity. So, when a heavier body is hitting lighter body, the lighter body is gaining double the velocity, but the heavier body continues with the same velocity. A nucleus is hitting a neutron at rest. A neutron gets double the velocity, whereas the nucleus moves in the same direction with the same velocity. How to prove it? When a heavier body here, M1, is colliding a lighter body at rest. So, if you write E2 is equal to 0 and neglecting M2, in the above equations of V1 and V2, we get V1 is equal to U1 and V2 is equal to 1. This means the velocity of lighter sphere will be double that of the initial velocity of the heavier sphere. And the velocity of heavier sphere remains unchanged. So nothing happens to the heavier one. But the lighter one gains double the velocity of heavier one. That can be proved.